So I was eating beans with my dinner a while back, and I thought to myself, bean cans are made of steel. Steel is ferromagnetic. We can make something out of this. Now, when thinking about ways to create distributed energy, decentralized forms of energy, I thought, hey, a bean can would make for a good ferromagnetic material for a small generator. So with this in mind, and a lot of 3D printing later, I thought to myself, why not make a so-called BeanCanErator? A small generator made of, well, a bean can, plus a load of 3D printed parts. In theory, I could omit the bean can altogether and just use some magnets on a rotor and some coils. That wouldn't be very efficient because the lack of a ferromagnetic material means that the coils themselves won't generate a lot of current. Ferromagnetic material, which is usually some form of iron or steel or ferrite, kind of amplifies the amount of current generated by passing magnets across a coil of wire. Why such ferromagnetic materials are used in things like motors, generators, transformers, and lots of other stuff. To start off, let's do a bit of an inventory, shall we? So we have our bean can, we have these magnet holders that form the rotor of the generator. We have our bearings, which are encased in these caps, which will form the outer shell of the generator. We have our coil holders, which will hold the magnet wire in very much Blue Peter fashion. I already have a coil pair here, and this is going to be one of the coil pairs used in the stator. Also need some magnet wire. This is 0.4mm magnet wire, and we need, of course, for our rotor, we need our magnets. So let's get building. You might be wondering, why so many parts? Well, a design principle I'm very much in favour of, and that I try to employ here as much as possible, is design for disassembly. Take my rotor as an example. What I could have done is I could have just made a monolithic rotor, glued a bunch of magnets to it, and called it a day. However, I didn't choose to do it that way because the problem with that is that in today's world we use too much glue and too much adhesive for stuff where a press fitting or a screw or a trapped nut or something else like that could be sufficient instead. Instead, how this rotor works is you put your magnet in one half of the rotor. What you would then do is attach your shaft by pushing the shaft through the hole in the middle and then screwing it down via this trapped nut here. And then after that you would put your remaining magnets that cover the trap nut hole into the slots. Now what you would do is you would combine the two rotor halves, and after that you would, with a nut and bolt, you would secure the two halves together. Doing it this way, as opposed to assembling it using glue and other sort of easier solutions, means that this is very easy to disassemble, repair and recycle. And that's what makes things that are designed with disassembly in mind much more sustainable than things that aren't. Another example of this, again in my rotor half design, is these holes here align with the trapped nuts. And what this means is that if you can poke a thin object in there and with a bit of force you tap on said object, you can remove these trapped nuts. And that's something you don't really see in modern design, unfortunately. Otherwise, this would be a lot more difficult to recycle because these trapped nuts would just be embedded in there. But I've designed it so that we have a method to remove them. Now you might be thinking, in this part here, half of the magnet holes are the wrong way around. And technically, you'd be correct. And that's, on my part, intentional. The generator is basically a rotor with magnets on it, excuse me, I'm very bad at drawing. Just pretend these are magnets. And it's surrounded by a stator that's not perfectly aligned at all. And the stator consists of coils. Now here is how a normal magnet rotor is arranged. Imagine each of these are magnets and they alternate in between the poles. So one facing outward is north, one facing outward is south, north, south, north, south, north, south, and so on. I've just realised I've screwed up there. Nevertheless, this is a very, very simple way of manufacturing rotors for motors and generators and that sort of stuff. However, it isn't very efficient because while you have all of these poles, these active poles facing outward and interacting with your coils, you have all of this magnetic resource here that isn't being utilized and is just basically attracting itself to the shaft and not really doing much else. A solution to this inefficiency is something very, very cool and very, very actually quite simple to implement, and that is something called a Halbach array. Now, instead of having the regular arrangement of a rotor, so north, south, north, south, north, south, north, south, and so on, the way a Halbach array works is that it optimizes the amount of magnetic field that's being utilized. And it does this through maximizing the amount of area of the active parts of the rotor and minimizing the area of the poles that aren't being utilized. So here I've drawn a section of what is a Halbach array. And as you can see, we have a configuration of a magnet going sideways, so south and north, and then we have more area north because we have a magnet facing outward, northways, and then we have even more north because we have a magnet facing sideways where its north pole coincides with the north pole of the outward facing magnet and the sideways facing magnet before it. And these combine to form a larger north pole. Same thing here, except we have a large south pole and another large north pole, and so on and so forth. And if we look at the back or the inner part of the array, we can see that the amount of inactive poles, or the area of the inactive pole, is minimized. So we have a very, very little south pole here, a very, very little north pole here, a small south pole there, and so on and so forth. And what this means is that at least in a outrunner generator or motor, the amount of magnetic field, the strength of the magnetic field on the outside is going to be a lot stronger than the magnetic field on the inside, and that makes for much more efficient use of the magnets, which obviously means that with fewer magnets and a smaller generator size, we can generate more electricity. In terms of how we can arrange our coils, we have two options. We either have the Y configuration or the tortilla configuration, otherwise known as star and delta configurations. Now, there's lots of technical differences between these, and there's lots of debate in terms of what's better for what application and whatnot, but the main thing is to remember in terms of the differences between star and delta is that in a star configuration you have a neutral point that all of the phases connect to, whereas with a delta configuration all of the phases are sort of daisy-chained together in this triangular pattern. The main impact this has is that with a star configuration, if you're connecting line to line, then you can use a minimum of 2 phases, whereas with a delta configuration you can either connect single phase line to line, or you can connect all of the phases all at once to your application. As I said prior, there's lots of technical differences in theory between these two configurations, and they are better for different applications. They each have their own niche. Delta configurations are typically used in high power generators and large induction motors, whereas star configurations are, I guess, used for lower power applications, whereas the star configuration can actually be more applicable to our use case because we're working with imperfect inductors, and we're likely going to be working with imperfect loads as well. And if I recall correctly, the star configuration is quite good at compensating for that. So much easier to detect faults in a star system as opposed to a delta system. But before we get too lost in theory, let's get to actually building this thing. So I guess the first thing we do is remove the corporate branding from our bean can. Yes, much better. It looks nice and shiny now, apart from this bit. The next step is actually to make our bean can a little bit less of a bean can and more of a metal strip. And to do this, I just have to do what you normally do to open a can. Although, I don't think you want to, well, watch me open a can. So what I've done is I've used a can opener to remove the bottom cap of the can, and I've also removed the inner lip by just going over the bean can again with the can opener. Now that gives us this this hollow metal cylinder that we can then cut open into a band, and we can slot our coils onto. Although I still am yet to make the rest of the coils. So all I'm going to do now is take a hacksaw to this and open her up. So what I've done is I managed to cut a big score, a line down there, and I finished the job off with some scissors. Bear in mind, if you do this, these surfaces are very, very sharp, these edges rather, and so you have to be careful of that. But nevertheless, I think we have a clean cut considering how difficult it actually was, surprisingly, to get this apart. Anyway, what we can do now is we can sort of unbend this as such in order to try and get our coils to slot on there. And like so, the coils are going to snugly fit onto the rim or the wall of what was the bean can. And this is going to fit onto one of these caps, and that is going to form the stator for our generator. So now, using the magic of video editing, we're going to fast forward into the future, whereby I have, well, wound the rest of the coils. So what we have, after a crap ton of winding, is we have 3 coil pairs, effectively 3 phases. And what we're going to do now is we're going to label these up, if you can see all of them there. And what we're going to do now is we're going to label these up as A1, A2, B1, B2, C1, C2, and you'll see why we're doing that in a second. So with our coils, what we have is A1 and A2, we have B1 and B2, and over there we have C1 and C2. And now what I'm going to do is I'm going to place them onto our ferromagnetic material here, and what's important is the order that I'm going to be arranging them in. With your standard motors and generators, what you typically have is a coil pair, and each side of the coil pair is opposing each other. So A1 should oppose A2, B1 should oppose B2, and C1 should oppose C2, ideally. So what I'm going to do is I'm going to slot these in such a way that it's going to be A1, B1, C1, and then A2, B2, and C2. And then ideally, when this all comes together, each half of the phases will be opposing each other. So there we go, all 3 phases are placed on the bean can wall, and I've taken the liberty off camera also of placing, or rather slotting, the bean can wall with our coils on it into the slot on our cap for our stator. So now what it's time to do is go ahead and wire these up in such a way that it makes a star configuration. And the way we do this is we wire up all of the ends of one half of the 3 stator coils, and we leave the other end of the other half of the stator coils intact, at least for now, and that will form the star connection. There we've spliced A1, B1 and C1, we'll solder that later, and we have 3 open connections of A2, B2 and C2, if I can get it. Yep. Okay, so now it's time for the magnets and making our rotor. And a tip that I found quite useful for telling the pole of the magnets that you're using is just to use a compass. The needle that faces the magnet is the opposing pole. So right now the north pole, which is the red, right now it's facing north, and that means that this is currently facing south. This is the south pole. If I flip the magnet over, the compass will show south, and this means that this is the north pole. So what I've gone and done is label up all of my magnets north and south to easily recognize the poles. And now what I'm going to do is I'm going to take the holder for my rotor, and I'm going to place all of these magnets in the Halbach configuration. So here's the rotor. I didn't manage to successfully get all of the 12 magnets on because wrestling with trying to put magnets in a Halbach array is like trying to get your child up for school in the morning. But nevertheless, this should still serve as a good proof of concept for what I'm trying to show. So all we have to do now to complete the actual building part of the BeanCanErator is we just need to add our rotor to our stator and then cap it off with the other cap. So we have our bearing there. We're just going to slot the rotor into the bearing. So after I inserted the shaft with the rotor on it into the bottom bearing, I then capped it off with the other cap and then pressed that down. These aren't perfect fits. I will have to improve that in the future before releasing the STLs, but I took the liberty of soldering our neutral point. So this is now hooked up to our DVM. Well, one of the phases is, at least. And if we spin this, we get a little bit of voltage. Doesn't matter which way we spin it because this is AC. It's not generating much voltage, obviously, since I'm just rotating the shaft with my hand, and that doesn't translate to very much torque. So that's just this is just purely to test whether the thing actually works. So there you have it. We've made a functioning generator, or a BeanCanErator, from a bean can, and some 3D prints and some copper wire and some bearings and a shaft. But yeah, basically we've made a very fancy spinny thing. And now, because my hand isn't a very efficient way of generating energy, although I wish it were, we need something that can spin the spinny thing that we've just made.